Hey, what's up? It's Matt, and this is the companion piece to the Monty Hall problem that I uploaded on Conjecture. Go watch that right now if you haven't. This will make a lot more sense. So basically, like I said, this video was going to be, I was wondering what sort of conditions would have to exist within the context of the game, the Monty Hall problem, to make switching your door and staying with your original pick equally likely. Because in the problem, you should switch. You have a two-thirds chance of winning if you switch and one-thirds if you stay. But what are the conditions that would make those equal? So let's take a look at that. I'm going to make myself smaller, and now we've got some Photoshop drawing here. Great. So let's just start by, oops. So let's just look at the classic Monty Hall problem as a refresher. There are three doors. Behind one of them is a car. Behind one of them is one goat, and behind another is a second goat. Now, you pick one of these doors. You don't open it yet, but you pick a door and you hold on to it. Now then, Monty Hall says he's going to remove a door. Now, if you happen to pick the door with the car, then he's going to remove either, let's say, goat 1 or goat 2. It doesn't matter because they're both goats, right? And then the door you wind up with, or sorry, the door you can switch to would be goat 2 or goat 1. Either way, you get a goat. Now for goat 1, he's going to remove goat 2, which means the door you end up with is the car. And for goat 2, he's going to remove goat 1, meaning the door you end up with is the car. So the door selected here, this is the probability of winning the car if you just stay, if you don't switch, right? So staying, staying gives you 2/3 chance of a goat. And switching, so we can see here there's one car, two car, and a goat. And technically this is two goats at 1/6 chance each, whereas the cars are at 1/3 chance each. So that's a weird 6. Switching gives you a 2/3 chance of car. So switching is the better strategy. But now let's look at the conditions that I personally had wondered about. What kind of modifications to the Monty Hall problem would make the probability for staying with your original door selection and switching to the remaining door selection equally likely, instead of switching being better 2/3 to 1/3? Let's draw what's behind the three doors again. We'll start with car, goat 1, and goat 2, right? Now, the main reason why switching gives you an advantage in the normal version of this game is because Monty Hall removes a goat. He doesn't pick one of the doors randomly to remove. If the doors were picked randomly, that's when this could happen. Okay, so let me write this here. This is door selected. This, let me divvy this up. This here will be door removed, and this at the top will be door remaining. Okay, so if you have the car, either the goat 1 or goat 2 can be removed, right? And that means that goat 2 or goat 1 is left, right? And these have chances of that 1/6 and 1/6. Now for goat 1, if Monty Hall is indiscriminately removing doors, if he's not removing the other door that has a goat, then yeah, the car could be removed when you initially select goat 1, but also goat 2 could be removed. So if the car is removed, then the remaining door is goat 2. If goat 2 is removed, the remaining door is a car, which means here that switching, if you switch to the remaining door with goat 1, you only have 50% chance of getting it, right? Because this is 1/6 and this is 1/6. And then similarly for goat 2, I'm just going to draw the arrow base here. He could remove the car instead of goat 1 if Monty Hall is randomly removing these. So that's car, and that's goat 1. Let me, let me just move goat 2 so that it's more in line with this. Sweet. Okay. And then if you remove the car, that means that switching would give you goat 1, and if he removed goat 1, switching would give you the car. So 1/6 chance of this happening, 1/6 chance of this happening. So now if we tally up all of this top row here are the outcomes you get for switching, and this bottom row, because it's your initial door, are the outcomes you get for staying. So your outcomes with staying, as you can see here, are 1 win for car and 2 win for goats. So staying, just as before, means you have a 2/3 chance of goat, right? And now switching, because the doors are randomly removed now, instead of removing a goat specifically, there's 1, 2, 3, 4 out of 6 chances where you get a goat when you switch, and only 2 out of 6 when you get a car. So switching also means 2 out of 3 goat. So there you have it. That's really it. It's just, this problem is entirely based on the fact that the original problem is entirely based on the fact that Monty Hall knows which door he's removing. He knows that he's removing a goat, because it'd be bad TV to have someone play through the entire game to find out that their options for staying or switching were just goats, right? If he removed the car, then the person would be looking at him and go, well, why do I still want to play this? I don't want to win either of the prizes. So Monty Hall removes one of the goats, and that is what gives the player the edge in switching. But in this scenario where he randomly removes the doors, you no longer have an advantage, and switching and staying are exactly the same. So that's it. Yeah, that's it. Hope you enjoyed. I think these kind of diagrams are really fun and interesting, and just like probability mapping is what I'd call it. Yeah, that's all I got to say. Hope you enjoyed, and I'll see you soon.